Today will be the last day we talk about simplifying some forms of radical expressions, and we're also going to go into solving radical equations. Now you'll see in this first example problem we have 5 over the quantity of 2 plus root 3, and we've talked about already that you can never leave a radical in the denominator of a fraction. Now the problem with just trying to multiply in this case by root 3 over root 3 like we did in our previous example is in the numerator we get 5 root 3, but in the denominator we'd have to distribute that. We don't get to pick and choose what we multiply to. So I'd have 2 root 3 plus 3. These don't reduce because we have this addition, so we're going to have to come up with another way to get rid of that radical. Now, the way we're going to do this is we're going to rationalize by something called a conjugate. Now, what a conjugate is it's the same expression as the denominator, but with the opposite sign in the middle separating the two terms of the binomial. So in this case, I use the same two numbers to rationalize by, but I write the opposite of the sign separating the binomial. So instead of plus, I use minus. And notice what happens. In the numerator, I'm going to distribute. I get 10 minus 5 root 3. In the denominator, I have to FOIL because this is two binomials. So first, outer, inner, last. I end up with 4 minus 2 root 3 plus 2 root 3 minus root 3 times root 3 is 3. So you'll notice the middle term goes away because 2 root 3 plus negative 2 root 3 is 0, leaving me with 10 minus 5 root 3 all over 4 minus 3, which is 1, or 10 minus 5 root 3. Now, it's not always the case that your denominator will completely disappear. I can write 1 if I want, but it really doesn't mean anything to divide by 1 because it's just the same as the numerator. So again, not always will your denominator completely disappear, but what will disappear when we rationalize by the conjugate is that radical term. So let's do another one. So here I have an example of root 3 over 2 minus root 5. Since I have this radical in the denominator, I want to rationalize by the conjugate, so that's 2 and a root 5, but I need to have an addition sign between the two this time. Distributing through, I end up with 2 root 3 plus root 15 over, I'm going to FOIL, so that's 4 plus 2 root 5 minus 2 root 5 minus root 5 times root 5 is 5. So I have 2 root 3 in the numerator plus root 15 over, once again I have 4 minus 5. This ends up being negative 1. You can leave it like that if you'd like. So I have 2 root 3 plus root 15 over negative 1. Most books will go ahead and do this, negative 2 root 3 minus root 15. And again, unfortunately, didn't pick a great example for you because the denominator completely went away. There may be a denominator left in the end. So now what we're going to do, that was kind of it as far as simplifying radicals. We're going to solve some radical equations. So I have the root of x is equal to 6. Now because this is an equation, I can do whatever I want to both sides of the equation as long as I do the same to the left as I do the right. I want this root to disappear, and we've talked about anytime you multiply a root by itself, what comes out is what was under the root. So if I go ahead and square both sides, root x times root x is just x, and 6 times 6 is 36. So you'll notice my solution is 36, and if I take the square root of 36, I get 6. That's my check. Now, one of the rules that's going to hold throughout this whole thing is we need to isolate the root and square both sides of the equation in order to solve these square root equations. So isolate the root first, then square both sides of the equation. Theme of the day. Notice, My root is isolated on one side of the equation. Once that's done, I square both sides of the equation. I have root 3x multiplied by itself because it's squared. That's equal to 3x. And 4 squared again is 16. Divide both sides by 3, so x equals 16 over 3. Now in this case, the root isn't isolated. I'm going to isolate that first by subtracting 5 to both sides. So I get the subtraction of 5 to both sides, therefore root x plus 3 is equal to 4. And now I have the root isolated on one side of the equation. I'll take and square both sides. Root x plus 3 multiplied by itself is just x plus 3. 4 squared once again is 16. Subtract 3 from both sides, and x is equal to 13. If I wanted to check that, I could. 13 plus 3 in a root plus 5 should equal 9. And I have the square root of 16 plus 5, which is 4 plus 5, or 9. So it checks out. Again here, you'll notice the root is not isolated. I'm going to take and add 4 to both sides. So I have 12 is equal to 3 times the root of x plus 1. As far as I'm concerned, that root's still not isolated. I'll divide both sides by 3, leaving me with root x plus 1 is equal to 4. Square both sides again. Root x plus 1 squared is just x plus 1. It's going to equal 16. Subtract 1 from either side, and I get x equals 15. Next, you'll notice I have square roots on both sides. So in theory, the square root is isolated. If I square both sides, notice both of these will pop out. So I have 2x minus 1 is equal to x plus 7. Subtract x from both sides, add 1 to both sides. I end up with x equaling 8. Now in this case, I can't really isolate either square root. And the square root that I really want isolated is the root that has the variable in it. So it's this one right here. I'm going to square both sides. And since I'm squaring a rooted part of an equation, that's just going to come out of the root. When I square this, I have to say 3 times 3, which is 9, and root 5 times root 5, which is 5. So I have 1 minus 6x equals 45. Subtract 1 from both sides, and I have 44 is equal to negative 6x. Divide both sides by negative 6. And x equals negative 22 over 3. You'll notice on this side, again, the root is not isolated. I'm going to go ahead and do that by subtracting 4 from each side. These aren't like terms, so I end up with negative root 3x plus 28 is equal to x minus 4. But again, this root isn't isolated. I'm going to take and divide by negative 1 to both sides. I end up with 4 minus x is equal to the square root of 3x plus 28. Now I can square both sides of the equation. This term will pop out. But notice when I square this side of the equation, I have a binomial squared. I can't distribute that in. You can't distribute a power, so I'm going to have to FOIL, which means basically taking 4 minus x times 4 minus x. Leaves me with 3x plus 28 equals 16. minus 4x minus 4x plus x squared. Notice I have an x squared in my problem, therefore I'm going to have to set aside equal to 0. So I'm going to bring both these terms over to the other side. So I have 0 equals x squared. Going to subtract 3x. That's going to leave me with, there's negative 8 and negative 3, which is negative 11x. And I'm going to subtract 28 from both sides. And that's a negative 12. This is going to factor to x minus 12 and x plus 1 is equal to 0. Use our zero product principle. X minus 12 is equal to 0 and x plus 1 equals 0. Therefore, x equals 12 and x equals a negative 1. All right. That's really all I've got for you. I'd like you to write your lesson summary, answer the questions below, and we'll discuss this more tomorrow.